Right. Good morning, everyone. I'm Sally. I'm assistant professor in the Department of Physics at the University of Nevada in Reno. So first of all, thank the organizers for this amazing event. I've been enjoying our discussions during the program throughout, and also this week's conference. And it's a great opportunity to speak after Sarah. I feel like she has presented all my so I'm going to maybe take a slower approach and dive into some of the details of some of these experiments to talk about Southern Ocean teleconnection and also show some new results focusing on the impact from Antarctic meltwater input. So the outline here, I'm going to start by introducing the reason that I started working on this problem is really trying to understand the observed SST patterns, and then some lessons that we've learned, which Sarah also referred to earlier, from the Southern Ocean pacemaker experiments. And at the end, I'll talk about the future of Southern Ocean teleconnection, which focuses on the results from the SOFIA simulations. All right, so I got interested into this problem because of this map, basically the observed SST trends, and this is from 1979 to 2013. And so there are some very large-scale features on this map, mainly the zonal asymmetry in the Pacific, both the North and South Pacific, but also there's a meridional gradient in the Atlantic. We have more warming to the north and less so in the south. And then over the Southern Ocean, we have this broad cooling trend. So previously, people have tried to connect the tropical cooling to the Southern Ocean, and they have performed pacemaker experiments to try to contain or force the model to have this cooling trend in the tropical Pacific and to see its global impact. And actually, the impact on the Southern Ocean overall is quite limited. And if you're interested, I can show you this later. So you can even go back further in time. Of course, the coverage of data is not as good if you go further in time, but the late 1940s is kind of the earliest you can go if you want to look at the Southern Ocean sea surface temperature. And we see also some large-scale patterns, but they look quite different from the later period. So mainly here we have mostly meridional gradient in SSTs, large patterns, so cooling to the northern, in the northern hemisphere and more warming in the southern hemispheres. And particular in the Southern Ocean, we have warming, which is, there is some patterns, but overall we see a pretty broad warming in this period. So my question is, could we explain some of the tropical SST trends that is driven by the Southern Ocean trends during this period? And we know that the Southern Ocean SSTs can be influenced by a variety of factors, and here I'm not really trying to understand what is driving that SST variability over the Southern Ocean, but really to look at its impact. And to do this, we're doing the Southern Ocean pacemaker experiment. So how it works is that we choose a region that we're interested in to nudge, and in this case, we're choosing the Southern Ocean. So we nudge the SST in the fully coupled climate model at each grid point to the observed monthly anomaly plus the model's mean state. So we're trying not to change the model's mean state because that could create problems that we don't want from our simulations. And the rest of the globe is able to evolve freely. So it's just in a normal fully coupled mode. And then we can look at the impact of having these observed SST pattern or evolution on the rest of the globe. So if we look at the SST time series from the Southern Ocean, That's shown on the right. So the blue shading is showing the free-running CESM-1 simulations. So this is a 40-member ensemble, and you can see a pretty big spread, but they all seem to show a warming trend that is very different from what the observations show. And the observations are shown in both the green and black curves. So the observations, if you look at the trend and also towards the end of the simulation, is coming outside of the ensemble spread from CESM1 large ensemble. And to do this pacemaker experiment, after nudging the SST, the Southern Ocean temperatures are shown in the orange, which is hard to see by design, right? We're nudging the SSTs there, so it should follow the observations, and that's indeed what we see. All right, so now we can look at these simulations. It's an ensemble of 20 members, so we can really average to look at the ensemble mean to eliminate the noise from internal variability. So again, we're trying to explain the observed trends, and we know in reality, this pattern is coming both from internal variability and from radiatively forced response. So it's a combination of the two, and internal variability can include many things. For example, the Southern Ocean itself might have some decadal to centennial variabilities, some models, and there's some longer paleoclimate evidence that shows that. So that could be part of the internal variability. There is also the Pacific decadal oscillation and also the Atlantic meridional, Atlantic multi-decadal variability that will also contribute to this observed SST pattern. So this is the map that we get from the Southern Ocean pacemaker. So it's the average over 20 ensemble members. And what it's showing here is really a combination of the Southern Ocean driven response and the radiatively forced response during this period from 1979 to 2013. So again, the Southern Ocean looks very similar to observations by design, but then the rest of the globe shows still a very strong warming in this model, and there's very weak cooling over the Southeast Pacific. But because we're interested in the Southern Ocean driven response, we should subtract the radiatively forced response from our simulation. So this is what the radiatively forced response due to changes in aerosols and greenhouse gases look like in CESM1. And we see this very strong warming along the equatorial Pacific and in the tropical Atlantic as well. And if we remove that, we can get the Southern Ocean driven response, which you saw earlier that there's a pretty weak cooling that we see on the eastern side of the equatorial Pacific, which is actually not statistically significant. So the stippling show significant regions. Even after having 20 ensemble members, this is not able to give us a significant response in the tropical eastern Pacific. I also want to mention in the Atlantic, we actually see a more significant cooling, especially in the South Atlantic. And later in the talk, I really want to emphasize on the difference in response in the two ocean basins. So we can do the same for the earlier period, the Southern Ocean warming period, and I'm just showing all these panels. So again, observation, the actual Southern Ocean pacemaker experiment ensemble mean, and you see a very strong asymmetry in the hemispheres, SST trends, and that's mostly coming from the radiatively forced response. And again, I think this is related to aerosol forcing in this earlier period because it's from 1949 to 1978. So if we subtract that, we get the Southern Ocean driven response, which has a pretty broad warming in the equatorial Pacific. Again, it's not significant because that's just a region with a lot of internal variabilities. 20 members is not able to beat down that noise here. But in the North Pacific, we're starting to see this PDO-like pattern, so zonal asymmetry in the SST, where we have cooling to the west and warming to the east. In the Atlantic basin, we see warming in the South Atlantic and the cooling in the north. So we have this meridional gradient in the tropical Atlantic, which is statistically significant from our simulations. So we can quantify how much of maybe the observed internal variability that contributes to the SST trends can be explained by the Southern Ocean driven component. So that's shown here. So the bottom line here is that the Southern Ocean driven response can explain roughly half of the observed tropical SST trends due to internal variability. So I have subtracted the radiatively forced response in the calculation of the trends in two regions, so the tropical Southeast Pacific and the tropical South Atlantic. And here it's showing both the cool and warm period, and also I calculated the trend difference between the periods, and that actually is allowing us to beat down the noise further to get a more statistically significant results. So if we compare the green with the black, that's showing the contribution from the Southern Ocean driven response, and we get roughly a third for the Pacific and more than half in the tropical South Atlantic. So this is really, if we want to put just some numbers on the impact of observed Southern Ocean cooling, this is kind of the results that we get. All right, so next, I want to focus a bit more on these difference in the two versions of our pacemaker experiments. So the response in CSM1 is quite weak, and then this really nice schematic has highlighted the role of subtropical low cloud feedback. And to further look at how different processes contribute to the teleconnection, we can use the surface energy budget, which is a very simple equation that governs the SST evolution in the mixed layer. So on the left-hand side, we have the heat storage term, and then on the right-hand side here, I'm decomposing it into the radiative fluxes and the turbulent heat fluxes, and then the term due to ocean dynamics. So we can linearize the latent heat term and diagnose the SST, assuming that on longer timescales, if you look at a 30-year trend, the heat storage term is negligible. So that allows us to do this decomposition, and we can really look at the influence of processes such as low cloud feedback or wind-driven, the wind evaporation SST feedbacks on SSTs. So this is, again, the Southern Ocean driven response from the first pacemaker experiment from CSM1. And if you look at the shortwave component, you see some very similar patterns in the regions where we see this cooling. So both along the coast of South America and the coast of Africa, we see this cooling, and these are hotspots where the stratocumulus clouds are very active. And then the ocean heat transport term is giving us cooling in the equatorial Eastern Pacific and also in the equatorial Atlantic. And the last term that also has a pretty strong contribution to SST is the wind-driven latent heat flux. And overimposed here, you can see the wind vectors showing the wind anomalies. And what you see here is really in the subtropics and in the equatorial Atlantic, the strengthening of the climatological winds, which leads to more surface evaporation, which further enhances the cooling. So these three terms are the main contributors of SST anomalies in the CSM1 Southern Ocean pacemaker. And if we look at the second version with CSM2, the Southern Ocean driven response is overall much stronger. There's also very interesting asymmetry in the two ocean basins where the Pacific is just much stronger than the response in the Atlantic. And if we look at the shortwave component of the heat budget, the signature in the Pacific is just overwhelming. the SST contribution, and we have very strong values due to this very active subtropical low cloud feedback. The ocean heat transport is acting to counteract the cooling along the coast, at least. So in both ocean basins, it has the opposite sign to the shorewave term. So this is a pretty interesting thing that we found. And then if we look at the wind-driven latent heat contribution, it's also very strong, but further away from the coast in the subtropics where the climatological winds are very strong and strongly enhanced in this situation. So the heat budget composition has dramatically changed when you increase the strength of the low cloud feedback in the coupled model. So a summary of that is really to do an average of those terms, focusing on the Southeast Pacific triangular region. And going from CSM1 to CSM2, you're really seeing an increase of this shortwave contribution. And there's also an increase from the red to blue in the latent heat term. And then the oceanic heat transport really acts to balance out that very strong cooling coming from the shortwave term. So in net, we actually have a much strong cooling using CSM2. And this Kim et al. Study really helped us to put the different climate models in terms of their shortwave feedback strength. So it's a really nice table. You can see the observed values that Sarah also pointed out. It's around 7.5 in the Western South American coast in the Pacific. And if you find where CSM1 and 2 are, they're kind of on the two ends of the spectrum where it's super strong in CSM2 and pretty weak in CSM1. So this is really, doing these two pacemaker experiments really made us think the role of the subtropical low cloud feedback, also why it's influencing the tropical Pacific very differently compared to the Atlantic. Right. So now we have this really great opportunity to further look at the intermodal spread of this teleconnection from the SOFIA simulations. So I'll introduce these a bit if you're not familiar. So this is the Southern Ocean Freshwater Input from Antarctica initiative. It's aimed to compare the model response to added freshwater forcing that is motivated by projected Antarctic ice melt. So we here focus on the Antwater experiment, which is an idealized experiment. So there's a freshwater flux anomaly of minus 0.1 Sverdrup applied at the ocean surface along the coast of Antarctica. Again, it is idealized, so it might not represent the exact process where the fresh water is released, but again, it's a very good first pass at looking at the impact. So just to provide some context on how big this freshwater forcing is, these are some curves from showing the freshwater input from the two different scenarios from the ISMIP simulations. And the blue is the more moderate scenario, and the red is kind of the SSP 585, so more aggressive scenario. And the Antwater, which is idealized, is held fixed throughout the simulation, is at a magnitude that is much stronger than the moderate scenario, but weaker than the end of the century projection for the aggressive scenario. So we can look at the multi-model mean and as well as the individual models response from these 100-year simulations from the Antwater experiment. Right, so this is where the title came from. So the robust part is really that models agree on the sign of the response, both in their temperature, air surface temperature and in precipitation. So the top, we see cooling that, of course, is the strongest over the Southern Ocean, but also propagates into the lower latitudes. And whenever there's stippling, it's showing that all 7 models analyzed here agree on the sign. So most of the globe, all models show cooling, apart from the North Pacific and the North Atlantic. These regions, the models don't really all agree on the sign. And the multi-model mean shows some warming in these 2 regions. And then the bottom is showing precipitation. And again, we see a very robust northward shift of the ITCZ in both basins. So the hatching here is when all models are showing a positive precipitation anomalies. So that is the case across the tropical Pacific and also across the Atlantic. And the purple line is showing the climatological precipitation from the multi-model mean. So that's the robust part, and the diverse part is really the magnitude. So on the right, I'm showing the zonal mean temperature and precipitation anomalies. And if you look at over the Southern Ocean, there's a very large spread on how much cooling there is. So it ranges from minus 1.5 to minus 3 Kelvin. And that large spread is quite interesting. And if we go further north into the tropics and even into the Arctic, there is also uncertainty on the magnitude of that teleconnection. So the precipitation, similar to what we saw earlier from another multi-model intercomparison experiment, models just don't really agree on the precipitation response. They all show this peak in the north of the equator of enhanced precipitation, but the drying to the south, both the magnitude and the location of the peak vary a lot across models. All right, so there are 2 key tropical indices that I'm interested in here. The first one is focusing on the equatorial Pacific. This is really looking at the equatorial Pacific zonal temperature gradient. So this is a proxy for the Walker circulation as well as the pattern effect for climate sensitivity. So the left is showing now the x-axis is longitude, and the y-axis is showing the surface temperature anomalies. And most models show a strengthening of the zonal gradient. So this is the warm pool and this is the cold tongue. So climatologically, this is warmer and the models cool less in this region and cool more around the cold tongue region, except for one model which shows a pretty complicated zonal pattern in the temperature. And then on the right is another index focusing on the Atlantic. So I mentioned earlier that the meridional gradient of the Atlantic is really important. It's correlated with the AMV as well as the tropical cyclone variability and Sahel precipitation. So all models here show a positive meridional temperature gradient in its temperature anomalies. But again, the magnitude has a very large spread. So we can calculate these 2 indices, just calculate one number for each model and look at how these 2 indices vary across the models based on their strength of the subtropical low cloud feedback, which earlier has been identified as a key driver of the intermodal spread. So again, it's not a lot of dots here, so it might not be super telling if we can add more models, but based on these 7 models, we can see a very strong positive relationship in both indices. So this is the zonal gradient, and this is the Atlantic meridional mode. And here, the dashed and solid lines are coming from observations. So now we have models that underestimate the subtropical low cloud feedback, which has a weaker teleconnection, both in the Pacific and the Atlantic, and the one model, CSM2, that has a super strong cloud feedback, which has a very strong teleconnection. And I forgot to mention here, I'm showing a ratio to the Southern Ocean anomalies. So it's trying to normalize the fact that these models also show very different cooling over the Southern Ocean. And not all models have multiple ensemble members. And for the ones that do, I think it's also pretty interesting to show how variable they are. After 100 years of simulation, you still see a lot of spread especially in the tropical Atlantic, how much internal variability contributes to the anomalies at the end of the simulation. So maybe we should definitely, even with this idealized experiment with a relatively strong forcing, we should take into account of the noise in the system due to internal variability. Right, so we have fortunately 2 models that provide further outputs to look at their heat budget. So I've selected CSM2 and Access. One has a strong shortwave cloud feedback and the other one has a weaker shortwave cloud feedback. So we can look at the evolution of the surface heat budget in both the tropical Pacific and Atlantic basins. So this is from CSM2. And this is the ensemble mean of the 3 members. Actually, the 3 members look quite similar in terms of the patterns towards the end of the simulation. So very strong cooling along the equatorial Pacific, as well as cooling in the South Atlantic. So we average the 2 boxes here, one on the eastern side of the equatorial Pacific and the other one in the South Atlantic. And then we can compute their surface heat budget. And at the end of the simulation, in the Pacific, the cooling is mostly coming from the shortwave term, which is related to the cloud feedback, as well as the latent heat term, which is mostly wind-driven. And it's balanced, counteracted by the ocean dynamics and the long wave terms. And in the Atlantic, actually, the shortwave term towards the end of the simulation has very little impact on the cooling, and it's mostly coming from the latent heat term, which represents the west feedback. So that's the quasi-equilibrium response. But if you look at the beginning of the simulation, they actually show also very different compositions. So this is still work in progress, and we're looking into ways to use the heat budget to provide some insights on which physical processes contribute to the cooling and why there's such a big asymmetry between the 2 basins. For example, in the Pacific here, in the first year, we have a very strong warming, and that's coming from both the ocean and also the shortwave terms. So both terms actually contribute, where the latent heat term is acting to provide a negative SST anomaly. And that's not the case in the Atlantic. So this, remember, is the model with very strong shortwave cloud feedback. And the cloud feedback should be strong in both the Pacific and the Atlantic because they're both hotspots of subtropical low feedback, but actually low cloud feedback. But that term actually has very little contribution here in the Atlantic. So for the next model, Access, it has a weaker shortwave cloud feedback, but we actually see a more pronounced contribution in the tropical Atlantic. So this blue curve is contributing to the cooling in the tropical South Atlantic. So that's really interesting. Even this model has a weaker cloud feedback. It actually provides more cooling in the tropical South Atlantic as opposed to CSM2. All right, so to summarize, I've shown that the Southern Ocean SST variability can explain a very significant portion of the observed tropical SST trends, and the strength of the teleconnection, again, confirms that it depends strongly on the subtropical low cloud feedback. And the surface heat budget analysis actually reveals potentially different teleconnection pathways in the Pacific and the Atlantic. And I think I would really be interested in looking further into this issue because so far I think a lot of the focus has been on the Pacific basin only. So thank you.
Any questions for Sally?
Yeah, thanks for a great talk. So I was interested in the Northern Hemisphere warming that you see in the last part of your talk, and I was curious if you've looked at if there's any role for AMOC changes. I'm not sure how long these experiments are, but it kind of looks like it could be possible that with some extra cooling, you would have a stronger AMOC, and we'd expect that to like warm the North Atlantic and yeah, just Northern Hemisphere disproportionately. But yeah, curious if you looked into that.
Yeah, thank you. So there is a study specifically looking at the impact on AMOC from this Meltwater experiment. So I highly suggest you to check that one out. But I haven't looked at here the impact of AMOC on the Northern Hemisphere temperature. But I do want to mention that there is more uncertainty. So not all models show these warming patterns in the North Atlantic. So yeah, it's probably very model dependent.
Cool, thanks.
Hi, Sally. Very nice talk. Thank you. I was just interested, do I remember correctly that Sophia ran 2 sets of experiments, one where you have the freshwater right on the coast and one where you distribute it? Are these one of those or?
Yep.
Yeah.
So these are when the water is distributed along the coast only.
Just right on the coast
Yes.
and right at the surface
Yes.
is the input? Have you looked at all at the distributed ones?
No, I think I'm not sure if that was tier 1, but
Okay.
so far I think the most models have provided this more idealized version of that, or the other one is idealized too, but this is the one that has the most model outputs.
Okay.
Yeah.
But
it
I
will
would be
interesting
interested to see what happens if you like put a more realistic freshwater mask on.
For sure. Yeah, I think they have multiple tiers of experiments and they have already started tier 2 simulations. So I'm really looking forward to more simulations coming out of that initiative and looking at the teleconnections there.
Great.
Yeah.
Thank you.
Great talk, Sally. I'm curious about those plots you showed in the Meltwater runs where you show the dependence of the tropical response on the cloud feedback. Yeah, so if I remember, you normalized this by the Southern Ocean SST response. I'm curious if you didn't do that, like would the plots look similar? And I guess what I'm getting at is are the models that have the strong cloud feedbacks, do they happen to also be the ones with stronger Southern Ocean SST responses? And that might tell you something about the possibility of this being somehow a two-way connection. Because as you know, I've looked at these Meltwater runs too, and I could never pin down a mechanism for that spread in the Southern Ocean SST response.
Yeah, the short answer is no, they don't look like these. That's why we decided to show the ratio, and it's kind of, the ratio is representing kind of the efficiency of that teleconnection if you compare to the Southern Ocean anomalies. But I agree with your point. Like the Southern Ocean response itself has already such a strong model dependency. And then the tropical signals, you can kind of tell here, or maybe here. Well, yeah, in the zonal mean plot, models that have the strongest Southern Ocean cooling don't necessarily have the absolute strongest magnitude of that tropical cooling here. But after normalizing against that, you can actually show the relationship that is much stronger. Yeah.
Still a mystery what's causing that big spread in the Southern Ocean.
That seems to be a very important question. Maybe people should attack that first from these runs. I'm surprised that it hasn't been solved.
Thank you.
Thank you.
Cool. Thank you, Sally. They're pretty clarifying questions. The first one is just about the Meltwater experiments. When you're showing here these time mean anomalies, is that reference to reference simulations where there is no meltwater or where there is like current observed rates of meltwater, for example?
Yeah, so they're referenced to pre-industrial control simulations where there's no meltwater.
No meltwater? Okay, I mean, Antarctica is always carved and basal melted, but that's okay. And the other one was, I probably should have asked in Sarah's talk as well. I don't understand the number that is being used to quantify the magnitude of this cloud feedback. It doesn't.
Yeah.
Can you explain what that is?
Yeah, for sure. So I cut off the units, but these are in watts per meter square per Kelvin. So it's kind of that TOA perturbation due to cloud. So it's you can think of it as calculating the cloud radiative effect and then normalized by local temperature changes.
Okay.
Yeah.
Cool.
So it's the sensitivity of the TOA shortwave.
Thanks for the nice talk, Sally. This is a question about the mixed layer heat budget that you did at the beginning. So as an oceanographer, we only get one letter O.
Yep.
So
totally.
Would you be able to talk a little bit about what is happening in O? Is it vertical heat flux divergence, horizontal heat flux, Ekman dynamics? Like, have you dug into that at all?
Yeah, I was expecting this. But so when I did the first pacemaker experiment, I did compute the Ekman due to Ekman transport, and that term can explain the equatorial anomalies from this residual term, but we never got to compute the full ocean mixed layer heat budget. So including like the horizontal advection terms explicitly or the entrainment or vertical terms. So it would be great, I think, to further decompose this term, because as you can see in especially CSM2, it has a very strong anomaly to counteract the short wave, and it will be great to know exactly what process is driving that strong.
Do you have all the terms to do that?
I'm not sure, no. Sarah says no. But I think in Sophia, it might be possible that we only have monthly mean velocities and temperature terms. So I would love to get your idea on whether we can compute that.
Great, thanks very much.
Yeah, thank you.
Hi, Sally.
Hi.
Great talk. So one question following up on Ruth's question. So you showed that there's a big difference in the cloud feedback between CSM1 and CSM2. Is there a simple explanation for that? Is it differences in the parameterization or number of clouds in the mean state?
Yeah,
or something else?
So based on my understanding, there has been a very big change going from CSM1 and 2, from Chem5 to Chem6, and including cloud microphysics and aerosol cloud interactions. So that is the biggest change that I know going from CSM1 to 2, because the ocean model is basically the same version, same model. So the atmosphere is really the reason that the response is so different. But I'm really curious. So if you look at, I think I have a map. This is only CSM1, so I don't know how it looks like in CSM2. But if you look at the cloud feedback computed for the globe, it's very strong in this region, which we think is really important for the teleconnection in the Pacific. But it's equally strong in the Atlantic. That's another region where the subtropical low cloud feedback is important. So if you change the model's physics or parameterizations, it should impact all regions equally, but it seems to only affect the teleconnection in the Pacific, which is really puzzling to me. Yeah.
Okay. I guess I can ask a second question.
Yeah.
So the Sophia experiments seem to make a strong case that Antarctic meltwaters are pretty important climate force on maybe long time scales, but also transient short-term time scales. Do you have any thoughts on like how we may go about implementing this, like meltwater in regular sort of CMIP class runs?
Yeah. So I think that's a really good question, and So if you look at the historical values estimated from ice sheet models, they're actually really small compared to the Antwater experiment. So I suspect that it's not going to have such important drivers in terms of the teleconnection. But projecting into the future, it might become increasingly important. So I actually don't know what the model developers or people who develop CMIP protocols will implement this, but I do think it's important to include some aspect of this in future simulations because that can also impact the projected tropical temperature trends. But yeah, I don't have a good answer for that.
Just jumping in very quickly, I'm going to talk about that tomorrow.
Oh, perfect. Yay.
Thank you.
Yeah, look forward to it.
So Sally, great talk. My question is, so, you talked about the changes in the stratocumulus clouds, and so I guess one question is, for these SOFIA experiments that are showing these differences in the Pacific and Atlantic side low clouds, are those historical aerosol forcings that you're using? And then I guess I'll just ask my second question, which is, if so, then could it be cloud aerosol interaction differences that are causing the differences between the Pacific side and the Atlantic side in the responses?
Yeah, so these experiments, so it depends on how the aerosol forcing looks in the PI control, because the Antwater experiment only adds meltwater. There's no other changes in radiative forcing. So I feel like the aerosol shouldn't drive such a big difference here if you don't really have an aerosol forcing in these experiments.
Okay, so they're using pre-industrial
Yeah.
aerosols? Oh, okay.
Yeah, they're using pre-industrial aerosols. Yeah.
Thank you. Let's thank Sally again, and really appreciate the two